Hello everyone, thanks for watching this video. Today I'm going to talk about our work DDS2M, which is a self-supervised spatial-spectral diffusion model for hyperspectral image restoration. Now let's start from the background of this work. First, we introduce the famous work DDPM. DDPM is a generative model that aims at learning a model distribution to approximate a data distribution. It is defined as a Markov chain structure that has the joint distribution shown in PPT. Based on DDPM, an image restoration framework DDRM is proposed. It uses a Markov chain structure conditioned on the degraded image. Another line of background is DIP, which is a pioneer of untrained neural networks. The key idea of DIP is that a proper neural network structures are reasonable priors of certain types of images. The following is an elaboration of the proposed method DDS2M. Our motivation is that existing diffusion-based methods are excessively dependent on the adversity and the quality of the training data and often focus on a specific domain. As a result, these methods may perform very well in distribution, but can be quite susceptible to distribution shifts. This is particularly inappropriate for data-poor applications, such as HSI restoration, where very limited HSI are available for training. So one remedy is to use the untrained neural network. This is a comparison of DDRM and our method DDS2M. We can observe that DDS2M utilizes a denoising network pre-trained on a large number of actual training data to reverse the diffusion process. In contrast, our DDS2M works by inferring the untrained neural network's parameters during the reverse diffusion process, only using the degraded HSI without any actual training data. This is the framework of our method. Our design mainly lies in the variational spatial-spectral module dubbed as VS2M at the reverse diffusion process. In VS2M, an HSI is first factorized into abundance maps and members. Then we utilize untrained UNet and FCN to model these two factors, respectively. In this way, the underlying HSI can be represented by the untrained neural networks, and the variational inference-based loss function can be obtained by maximizing the variational lower bound of the low likelihood objective. Considering the forward diffusion process, this loss is essentially a diffusion denoising objective. As for the VS2M-aided reverse diffusion process, we first perturb the degraded HSI Y where the forward diffusion process up to T0, where T0 denotes the step that the reverse diffusion process starts from. In this way, our reverse diffusion process can be easily obtained based on the reverse diffusion process of DDRM. Now let's go to the part of the experiments. We test our method on three tasks: noisy HSI compilation, HSI denoising, and noisy HSI super-resolution. We can observe that our method has shown the best reconstruction performance. The conclusion of this work can be summarized as follows. First, this work reveals a new insight into how to synergistically integrate existing diffusion models with untrained neural networks and put forth the first self-supervised diffusion model, namely DDS2M. Second, by virtue of our proposed VS2M, the diffusion process can be reversed solely using the degraded HSI without any actual training data. Third, benefiting from a self-supervised nature and the diffusion process, DDS2M admits stronger generalization ability to various HSI relative to existing diffusion-based method and superior robustness to noisy relative to existing HSI restoration method. Thank you for listening.